Good morning. I'm Alex Marty with Colton Noble. We're Lab Group 6B Thursday mornings, and we're doing Lab 6 today, which is off-axis aberrations, and we're going to be measuring the coma and astigmatism in a test lens. And before we show our setup and what we're going to be doing in this lab, I'm going to explain what coma and astigmatism are. So coma results is an off-axis aberration, and it results from the magnification varying with pupil radius. So what happens is when we have light coming in from some field angle, the rays do not intersect all at one point, and it results in a spot that has this kind of cone shape coming off the bottom of it. And astigmatism is a result of the tangential and sagittal directions of the lenses having different focal lengths. Our spot changes as we move between the two focus points, from having a straight line in one direction to having a straight line in the other direction. And now Colton is going to talk about our lab setup.
And so I'm going to show you our basic setup here. We have our laser, we have our microscope, objective, spatial filter, so we're spatially filtering the light, our collimation lens, a fold mirror, and the fold mirror, after the fold mirror is where all the cool stuff happens. We have a collimated beam going through a lens here, which is focusing rays of light into our microscope. And what we've done is, since we actually want to measure the coma and astigmatism using the Hartmann screen, is that we placed the Hartmann screen right over the top here, and you can see that there's 4 holes in there, 5 holes. So this creates 5 pencil beams at various pupil coordinates across the lens. The basic gist of what we're going to do is allow these pencil beams to go through the lens, and we're going to artificially create an off-axis field by moving this microscope over 5 millimeters. And once we've done that, and we see the light going back through, we can actually measure where each of the pencil beams comes into focus and where it lands with respect to the rest of its beams. And that'll allow us to go back and calculate what the coma and astigmatism looks like. Okay, and so now what we're looking through is the pencil beams going through the microscope, and they're hard to see, but you can see 5 of them all centered around the crosshair of the microscope. And I'm going to push them all together, and then you can see a nice fine, almost interference-like cross-section, showing that we are now on axis with their setup. We are now going to go ahead and move this off axis and conduct our experiments, and later we'll show you what our results are.
Alright, I'm going to talk about how we measured the tangential and sagittal coma of our test lens. So we have our Hartmann mask, and it has the center hole and then 4 outside holes. And we have generated our artificial off-axis field, as Colton talked about. And what we do to measure the tangential coma is we send the light through only one of the outside horizontal holes, and then we move the microscope along the Y direction until our beam becomes focused back over the crosshair, and then we record those positions, and that distance from where the center hole is over the crosshair to where the outside holes are over the crosshair should be the same for both of the outside holes if our alignment was perfect. It was a little bit off for us. It was about 35 microns difference, which is pretty good, and we found that the tangential coma was about 760 microns for this lens. And then we repeated that procedure, but using the top and bottom holes of the Hartmann mask, still moving the microscope in the Y direction, and that gives us the sagittal coma. Again, if our alignment was perfect, we wouldn't have any sagittal coma because coma is rotationally symmetric, but we found that there were about 50 microns of sagittal coma, which is a lot smaller than the tangential coma as we would expect.
So the next thing we did was measure the astigmatism. And so in order to do this, we let all of the light go through the top hole and the bottom hole, and we found out where the focus was for those 2 holes. And then after that, we covered all the holes except for the horizontal holes, and then we established where the focus lied on the horizontal plane. And so since we now have the focuses on the horizontal and vertical planes, and we can find the difference between those 2, we can establish what the astigmatism is. We found that we had an almost unmeasurable amount of astigmatism. It's only a micron or 2, or even 0. After measuring the astigmatism, we did different field angles. So we actually measured astigmatism and coma at 5 millimeters off axis, 3.5 millimeters off axis, and 0 millimeters off axis. At 3.5 millimeters off axis, we showed that the coma was less than it was at 5 millimeters, and we also showed that the astigmatism was still remained 0. And at 0 millimeters off axis, we showed that we had no coma and astigmatism.
Okay, so here are our plots. The blue line, the most dramatic one, we have our tangential coma. The red one beneath that is sagittal coma, and then going along at 0 along the x-axis is astigmatism in green. As we said before, our astigmatism was not measurable. We couldn't measure any, so that's why it's going along 0. Sagittal coma was very small, as we expected. We explained that before, so it just barely goes up. And the blue line, the tangential coma, follows the parabolic shape that we expect from tangential coma, which is good. So we're going to compare these graphs to what code 5 gives us when we put in the lens prescription off of the Newport website and see how close we are in the post lab. So that's it for Lab 6. This is Alex and Colton. See you next week.